Hey friends, Vincent here. Welcome to Fearless in Rust, where we make Rust clean and simple. Let's get into it. Today, we're taking a first look at a critical concept in modern cryptography, key derivation functions, or KDFs. A key derivation function is not an encryption algorithm. It's a transformation step that happens before encryption even begins. And, surprisingly, this step is where many real-world security failures actually occur. Let's start with what goes wrong without KDF. So, imagine a beginner write this. Password equal, let's say, secret 123, and key for AES equals the same. So, at first glance, this may look reasonable. AES is mathematically secure, so using the password directly as a key seems convenient, but this is cryptographically broken, even if AES itself is perfectly implemented. Why? Because human passwords are not designed to be cryptographic secrets. They usually have low entropy, predictable structure, presence in leaked password databases, and very limited randomness. So, an attacker does not try to break AES. They simply try millions or billions of likely passwords until one works. Modern hardware can test enormous numbers of guesses per second. So, the encryption algorithm is never the weak point, but the password is. This is one of the most real-world cryptographic failures. Now, this is where key derivation functions come in. A KDF converts a weak human secret into a strong cryptographic key suitable for algorithms like AES or ChaCha20. Think of it as a bridge between two worlds. You have human password, then KDF, key derivation function, and cryptographic key, and then encryption algorithm. So, a KDF protects symmetric encryption by doing three important things. First, it adds randomness using a salt. Second, it applies slow, repeated cryptographic operations. And third, it makes brute force attacks economically unviable. In other words, the attacker can still try guesses, but each guess becomes expensive. And when every guess is expensive, large-scale attacks become impractical. So, there are several families of KDFs used in modern cryptography. First, the PB KDF2. This is widely supported for legacy compatibility. Then you have Argon2. It is considered the modern standard for password-based security. Then you have Script. It is designed to resist hardware acceleration by requiring large amounts of memory. And then you have HKDF. H for HMAC based serves a different purpose. It derives multiple secure keys from an already strong secret. And this distinction is extremely important. So, for human passwords, use Argon2 or Script. For existing cryptographic secrets, use HKDF. They solve different problems and should never be confused. So, let's look at a small Rust example using HKDF. HKDF is commonly used after a secure handshake to derive separate keys for different purposes. So, we will use the crates HKDF and SHA-2. So, now let's start this example. Okay, so here we use the crates HKDF and SHA2. So use SHA2. Let's take that one and HKDF. Okay. So now in the make function, let's declare a sort. A few head type of 16 byte. Take like binary and reference. Let's take unit salt 1, 2, 3, 4. Okay. Oh yeah. Okay, so here a salt is a random value added to a secret before key derivation to ensure uniqueness. Salt is optional, non-secret, and should be random per context session. Now let's create an input keying material. So the same way. U8 32 and just let's compare that value. Okay. So at that point, EKM is the input keying material. The original secret given to the KDF. So it is the starting cryptographic material that will be transformed into one or more strong keys. In real systems, this comes from a handshake secret, a shared key, or anything else. Okay, now let's initialize HKDF. HKDF. So here we need the SHA256 constructor. And so here let's take as option reference of salt. Take and reference also from the input keying material. Okay, then let's allocate a 32 byte buffer where the derived cryptographic key will be written. So let's mute HKM. Take 0U8 and 32. Take up. Yep. Okay. And now we have to derive a new key for a specific purpose. Encryption key, ensuring key separation even from the same secret. So let's use the expand function. But the information let's use encryption key. And here we have a mutable reference of then let's unwrap. Okay, and now let's just print the derived key in hexadecimal format for readability. So println so OKM 2 so the X question mark, and here let's use the OKM variable. Okay, so now let's print the result. So take. Example, coding KDF. Okay, here we go. So each KDF expands an existing secret into new cryptographically independent keys. This allows systems to derive separate keys for encryption, authentication, and signatures, and avoid key reuse, and maintain strong isolation between cryptographic operations. Even though all keys originate from the same master secrets, they remain securely separated. Now, here is the critical rule you must remember. Never use password directly as encryption keys. Never. Always apply a salt, a slow KDF, and a modern hash function. Without this transformation step, your entire encryption system is compromised before encryption even begins. So, let's zoom out. Encryption algorithms like AES and ChaCha20 are extremely strong, but cryptographic systems fail when secrets are weak or improperly handled. Key derivation functions exist to ensure that real-world inputs, like passwords, become suitable cryptographic material. Strong encryption starts with strong keys, and strong keys often begin with a KDF. In this video, you've seen how KDFs protect symmetric encryption by transforming quick secrets into secure keys using well-established US libraries. Simple concept, massive security impact. Thanks for your time. See you in the next one.